So it's a pleasure to me to introduce Gabriele Arnulfo, again from the University of Genova, but from the Department of Electrical Engineering, I think. And he's gonna present a talk on long-range phase synchronization of high-frequency oscillation in human cortex. So Gabriele, please, the stage is yours.
So thank you, Sarah. Thank you all the organizers for this nice meeting and for the invitation. As mentioned, I'm Gabriele Arnulfo. I'm assistant professor at the University of Genova. And I'm talking today about this work that was a very challenging work. And it basically took 7 years of my life and the people that worked with me. The first observation of this phenomena that I'm going to describe today has been carried out in Helsinki when I was visiting Professor Palva in his group. And it took us 7 years to come up with a strong evidence of a genuine long-range phase synchronization in the human cortex. But what I'm talking here, everyone knows and have been told many times today and in the past days that the large-scale brain activity in the human brain is served with sensors that can be sensitive to electrical or magnetic fields, and it could be placed extracranially in non-invasive imaging, or it could be used in some pathological scenarios, like in epilepsy, for instance, by using intracerebral implants that Professor Nobili showed us in the opening lecture. The temporal variation of the electrical fields represent the actual cortical processing, and those variations can be observed with a very different temporal or frequency profiles. What is really interesting in our results is that a high gamma activity has been thought to represent active cortical processing, and as a proxy, as a local frill proxy of the synchronized firing activity, like the multi-unit activity you would be able to depict with microelectrodes. And the cortical sources are thought to be, the cortical sources of the recorded high gamma activity are thought to be recorded in approximately a volume that is 200 micron large around the contact itself. So within the high gamma frequency bands above 100 Hz, there is a vast coexistence of multiple forms of morphologically distinct fast activity that could be narrow band activity, broadband activity, and what is most interesting in our work, the fast ripple or fast electrical oscillations. There are multiple evidence that suggests that high gamma activity contains genuine high frequency oscillations, and that those are generated in the dendritic potentials and are promoted by a broadband spiking activity that is coherent and that is coherently enhanced by the synaptic potentials. So in this work, we hypothesized that the long-range synchronization of the high frequency oscillations arise from a large-scale brain network because the local synchronization in the high gamma activity endow local pyramidal cells population with greatly enhanced efficacy in engaging their postsynaptic targets. So this could be observable as an interareal increase in the high gamma in the high frequency oscillations phase coupling. And this would constitute a direct evidence, a direct indication of the spiking-based long-range neural communication per se. So we used stereo electroencephalography data in a very large population cohort to quantify the large-scale phase synchronization network in human subjects. So I'm not spend too much time in presenting you what a stereo EEG is, but basically I mentioned that stereo EEG is an invasive recording techniques that has been pioneered by Talleyrand et Bonco in the late 50s at the Saint-Anne Hospital in Paris, and is used in mapping the actual network mechanisms that propagate seizure that helps propagating the seizures in a drug-resistant focal epileptic patients. There are two aspects in stereo EEG that makes that very suitable for mapping the human brain. One is that has a very, very large signal to noise ratio because the electrodes are really close connected with the actual neuronal sources. The control is that it is really high invasive, as you can see in the image that I'm showing on the right side, that are very, very invasive. There are electrodes that are very long and that are stick deep into the brain, and the sampling and the spatial sampling is really sparse because it's very patient specific. So given the high patient specificity of the implant strategy of each patient, so we need a very large number of subjects to exploit stereo electroencephalography data in the human connectome mapping. And the other aspect is that the implantation is performed with the cranial volume closed and invisible to the actual surgeons that are performing the implants. So it's only possible to ascertain the actual recording position afterwards when the electrode has been implanted. So we developed and used this stereo EEG assistant that is a 3D slicer extension that aims at localizing on the pre-implant MRIs, the actual contact centroids that has been extracted from post-implant CT scans. There is a huge need of a large number of subjects to reach a correct sampling of the brain areas. So what we thought is that we actually in 2015 our initial cohort was composed of 27 subjects, and with that bootstrapping that sampling, we estimated that we would need at least 100 subjects to reach an accurate sampling of all the human connectome connection in these trio parcellations. So it took us 4 years to acquire 109 patients that has been divided in one main cohort of 19 patients. 68 of them has been analyzed and I'm presenting the results from. And an additional 11 subject has been acquired in a task cohort, and a smaller task cohort that I'm presenting later. All these observations has been replicated in 2 independent cohorts. One is from the Guarda Hospital, is a totally independent cohort coming from a different collaboration. And we also replicated our results in using Kai Miller's data in US, with mainly ECOG and few deep intracellular electrodes. So our cohort, as I was saying, our cohort, out of all the possible within hemispheric connections, representing in the Schaefer 100 resolution parcels, our cohort yielded roughly 80% of the left and 90% of the right hemispheric connection. So that provides us a very accurate sampling of all the possible interaction between all the brain areas included in the Schaefer 100 parcellations. What we measured, so we used 10 minutes of spontaneous activity recorded from different locations, and we used every possible contact is recording either from the white matter or the gray matter. That is impossible to understand or plan where each contact will be placed actually. So it's only possible with post-processing to understand whether one contact is recording from the gray matter and whether it's recording from the white matter. So our algorithm allowed us to identify whether one contact is recorded from actual neurons or their volume conducted activity. And we quantified the gray matter proximity index. That is an index that we proposed in 2015 that should tell us whether one contact is close enough to the gray matter boundaries or is located deep into the white matter. So for each gray matter channel, we referenced its activity to the closest one recording from the white matter that is used as a silent reference. For each pair of gray matter recording channels, re-referenced to their white closest one, we quantify the phase locking value across all the channel pairs. Using 50 frequency bands, it identified using Morlet filters with a ratio of 7.5. So the phase locking, I'm not going into details what phase locking value is, that has been presented many times. So just to say that the higher the value is, the higher the phase synchronization is across time. So what is very well known is that the phase synchronization in the human brain, in the resting human brain, adult brain, it has a huge peak that is around the alpha band. These data are eyes closed EEG data from electrophysiological data from human adult brain. So it's very well expected that is a peak of phase synchronization in the alpha band, and is mostly will be located in the posterior brain regions. So and these peaks and these phase synchrony spectra decays as the increasing of the frequency. What is completely unrepresented and previously haven't been reported in literature, only few suggestions and a few evidence has been presented in monkeys and rats and rodents mainly, but with a very smaller distances because the brain is actually smaller, you know. So basically what it was completely unexpected and took us a lot of time, a lot of effort to prove that this is not an artifactual effect, is that the phase synchronization decays, and actually after 100 Hertz, it rises back up, reaching levels of phase synchronization, reaching values that are close or very close to the lower frequency bands. The phase synchronization so is significantly enhanced, and it's not a product of volume conduction, because we replicated the same observation using the IPLV, so the imaginary part of the phase synchronization, the PLV that is insensitive to the zero lag, so the volume conduction component of the phase coupling. It's not a product of filtering artifact on the spike or the epileptic spike activities, as you can see here in the panel E, that a very in the time window where of the broadband activity, that is in the time window that shows the highest phase synchronization, that is shown here in the small inset of the zoom in of the time course. Corresponding to this small time window, there is nothing unphysiological or pathological activity that could explain these phenomena. That is clearly could be visually identified clearly in the time series. And more importantly, in the small panel, we have been showing the phase difference distributions, and you can see the phase difference distribution doesn't have a peak in zero lag, what would be representative of volume conduction or eventually of possible artifacts. Instead, has a mean phase angle that is roughly around minus 60 degrees. And it's not a product of the actual choice of a referencing scheme. So we add up the referencing scheme that we adopted is a novel scheme that we introduced in 2015. And it has never been, and it's only being used by us. So the bipolar recording, so where one contact is subtracted by the closest one, it's usually the gold standard. So it's not a product as saying volume conduction or spike artifacts, and not even the referencing scheme, because we could actually, by using the bipolar, we also have the classical bipolar, we still show clearly that there is a peak, a ramp up, and the peak again after 100 Hertz. And this is not a product of amplifier or acquisition noise, because we replicated a recording with electrodes immersed in saline solution, so there is no brain at all, and we computed the same pipeline with this saline solution data, and as it is shown here in the red curve, that is lying close to the surrogate levels. So given that all these analyses, additional analyses that we carried out are suggesting that our results are genuine, so we went further and show that the distinct PLV peaks, different subjects shows a distinct PLV peaks. So we classified, clusterized patients based on their their PLV spectrum, and we clusterize them basically in these 5 clusters. So where the most represented are cluster 1 and 2, where there are clearly visible peaks in the range of 150 and 210 Hertz or 230, 290 Hertz. We excluded for the further analysis the subjects from cluster 3, 4, and 5 because we couldn't see a clear peak, only a larger ramp up. So we couldn't, we considered this as an inadequate sampling resolution, or eventually to some sort of artifacts that we couldn't understand the actual origin. So we actually looked, so the further analysis we only represented in clusters that are considered more physiological and that are including only subjects from 1 and 2. We also showed that high frequency oscillation, the PLV is stronger between the, as kind of expected, between the limbic system, the frontoparietal system, and the fold mode network. There is a large also clustering within the visual areas, because a lot of patients have actual electrodes implanted in the visual areas because of the pathology, and this again is this task these recording are resting state with the eye closed. So we all know that visual areas in absence of actual stimuli tend to synchronize roughly to the alpha range. So for further understanding with the extent of our observations, we take advantage of the GMPI based the Great Macular Proximity Index classification, and we could that we advanced, and because of that we were able to separate contact pairs, picking up the activity from the superficial, most probably picking up the activity from the superficial layers or from the deep layers. And we then divided the contacts recording from either the superficial or deep layers, and made and test whether there is a significant difference between the coupling. So what we saw is that the high phase synchronization is mostly predominant in the deep layers compared to the superficial ones. That is in accordance with the knowledge that the alpha generators of the scalp activity are localized in the superficial layers, while the faster activity, so gamma and above gamma, are located in the central or lower layers of the cortical sheet. And this is kind of independent on distance. Also, one point that we wanted also to verify is whether the high frequency oscillations, phase synchronization was prominent in the background noise activity, or it was correlated with actual real amplitude increase, so actual burst of high frequency oscillation. So we performed an analysis where we pulled together all the channel pairs and divided their amplitude activity in quintiles, so that the fifth quintile represents the largest amplitude activity for that channel at that time, at that specific time point. And then for all those time points belonging to the two channels at that amplitude quantiles, we quantify the high frequency oscillation, we quantify the phase locking value for all the possible bands. So I'm here showing only the high frequency band that is comprised, basically that is comprised here in the 150 to 180 frequency range. As expected, so the high frequency synchronization is actually linked as more prominent in moments where there is actually an increase in amplitude. So it's not an effect of the background noise that is synchronized, but there is an active cortical processing. So there are spikes going on there. but we cannot avoid considering what happened, that these patients have actual pathology, that is pathology that is known to increase somehow cortical excitability. So we quantified two things. So the phase amplitude coupling between non-epileptic zone and epileptic and channels recording from the epileptic zone. And we showed that is significantly in the non-epileptic zone. So channels that are most probably recording physiological activity, because these are focal epileptic patients. So despite just the channels recording within the pathological networks, all the other networks are considered physiological. So channels recording from the physiological networks are showing a clear, significant phase amplitude coupling for the alpha band up to the high gamma frequency range. For the pathological case, we can see again that there is still this coupling, but is way more pronounced in the lower range and in the gamma range. That this is known effect that this delta theta activity is more during resting and far from the actual seizure onset. The slow oscillations are way coupled within the epileptic zone together with the gamma band. And further, we show that there is no significant coupling, there is no significant difference or significant enhancement of the phase locking value within the epileptic zone. So the red line represents channels recorded from the phase locking values of all the channels recording within the epileptic zone. And the blue one shows the channels recording from the physiological zone. So there is no significant increase in the short or long range between physiological or pathological. So we can conclude that that the high frequency oscillation, the phase synchronization of the high frequency oscillation is not a property, is not an exclusive property of the pathological network. So we wanted to understand whether this observation of a high frequency oscillation coupling is behaviorally relevant. So that then we asked 11 patients to perform a visual motor task, and we quantify the phase locking value, the dynamic phase locking value between the channels recording between all the channel pairs. So first, the task comprised 1,000 trial where we have 350 go and 250 no go, and this task is a highly response inhibition task that is known to involve a large frontoparietal frontotemporal scale activation network. So first we showed that there is actually an amplitude increase. So there is an amplitude evoked potential that lasts roughly from 200 milliseconds to 300 to 450 milliseconds in a very small portion of the activity. And we picked up the activity from all these. So we selected these channels for each of patient, and we quantified for all the channel pairs that are showing an actual amplitude effect. We quantified the dynamic phase locking value to understand whether there was an increase of the phase locking value after the stimulus onset compared to the pre-stimulus baseline. So what we actually saw that there is an amplitude increase that is transiently enhanced after stimulus onset, and that not all brain regions respond equally, but only few of them actually have an activity, and that the high frequency time resolved phase synchronization is significantly enhanced as you can see here, is significantly enhanced after the stimulus onset, only between the task positives, so those that are showing an increased peak, so there is an increase of phase synchronization, showing that there is only a positive, so an increase in phase synchronization, and there is not a decrease in phase synchronization. So just to briefly summarize, what we actually measured is that the high frequency oscillation are, as known, and ubiquitous physiological phenomena that actually reflects very local active cortical processing. As never shown before, long-range synchronization could possibly reflect there are messages that are relevant for behavioral and for behavioral responses that travels across the very large scale networks that reach distances up to several centimeters, several tenths of centimeters. Their high frequency phase synchronization is not a product of any artifactual sources that we can think of, including volume conduction or acquisition noises or muscle activity. High frequency oscillations are not a unique property of the pathological networks, instead are very prominent in physiological and in behavioral, and that are relevant for behavior and that because are enhanced in very short time windows that are prominent in the contacts that are considered actively responding to the task. This work has been a very huge effort for many people that, of course, the Ospedale Niguarda Milano, where we recorded the data together with Dr. Nobili, Francesco Cardinale, and Annalisa Rubino, and of course, all the people in Helsinki that are co-author of the paper and helped me like very much into the running this analysis. So all the authors and co-authors, and of course also my group in Genoa that helped me during these 7 years time to take care of all the other activity. So I thank you all the contributors and you for the attention.
Thank you very much, Gabriele, for this nice and inspiring talk. Let's see if there are any questions from the audience.
I have a small question.
Sure.
Maria Cala, please.
Thank you a lot for the nice presentation. I have maybe I think a minor technical question regarding the Theory G assistant. You were showing spheres, I think, representing the centroid of each contact.
Yes.
Is it? So did you take into account, would it be much work to include the actual cylinder instead of, so first of all, is it possible to export the spheres that you are showing here as
I mean, the spheres is just a visualization. We know exactly the coordinates of each centroid. So we know exactly, so we actually can compute things on these data. There is in the algorithm actually take into account the real physical dimension. So here we are showing for visualization purpose, we are just showing spheres. Although we know that are not spheres, are actually cylinders with a very definite dimension. So those dimensions are taken into account within the algorithm that they do the segmentation, but not here in the visualization.
Okay, I was thinking whether because if one would want to build a volume conductor, so a head model, then would it be possible just to have information from your tool to have exactly the volumes available somehow?
I did it at some point. I somehow lost the code that creates the 3D mesh in the many years that took me to create things, but I'm sure that would be possible.
Okay.
I'm sure that there exists in my hard drive this code that creates the 3D mesh for the actual electrodes.
I see.
I'm 100% sure. I only have to find it.
Yeah. Okay, great. And then maybe another small question. You are then localizing with the MRI, so to check in which layer each electrode is, each contact. I don't remember. You use, which is the tool that you're using? FreeSurfer or some other segmentation?
So we use FreeSurfer to do the cortical segmentation. Mm-hmm. And for assessing whether one contact is close to the gray matter or the white matter boundary, so it's handled within our tool in 3D Slicer, and that rely on the FreeSurfer segmentation meshes.
So you assume like some distance from the layer, from the surface.
Yes, it's just the the actual distance of the centroids from the nearest vertex in the white matter that is projected also in the gray matter. Okay. So the vector that connects the closest one in the white, that is, and that passes through the closest one vertex, the closest one on the gray matter, and then we project the centroids to this vector and compute the distance along.
Okay, yes. So you have both the surfaces, white and gray, and then you can measure the distance. Yes. Okay, thanks a lot.
Thank you, Maria.
I think we have a question from Andreas. I think you can unmute yourself. Yes.
Alberto was first, so if you don't know. I saw Alberto's hand first. If you want to go, Alberto.
Okay, you can. But I mean,
okay,
we have time for both. So
wonderful talk. Thank you very much. I have a question about the state of the subjects, not in the go no go. Actually, I have one there too. Was it the symmetric avoidance or just one stimulus, which could be either go or no go?
No, it was just one stimuli. Yes.
Okay. What about the rest of the data? Do you have any? The data, the electrodes are chronic, and therefore you must have a lot of sleep data. Did you look at sleep? Can you separate? Because that would be very exciting if we could know whether any of these frequencies or an entire frequency is present at different sleep stages.
So we had a very small cohort that was part of the original paper, that one of the reviewer asked us to somewhat remove or increase the number of subjects before doing any conclusions, because we only have like 6 patients or 7 patients there, where we recorded 10 minutes of REM sleep at the beginning of the sleep cycle, and 10 minutes of non-REM sleep at the beginning of a sleep cycle, and again 10 REM and 10 non-REM at the end before the waking up. So what we saw, like preliminary results there, suggest there's an increase in the phase locking value within the spindle high frequency bands that are prevalent within the limbic system. That is very, very nice and very robust, despite the fact that we only have 6 or 7 subjects. But we were actually trying to collect more data together with Professor Nobili, but then pandemic strikes out and everything blocked. So we can't acquire anything, and because the Ospedale Niguarda Milano nowadays, all the activity has been blocked for many times now. And so we have to wait when situation would be more simple to handle for
That's very exciting. I don't want to take any more time, but any more information you may have on that, I would appreciate just to know. Thank you very much.
I will contact you as soon as I have new results. Also, I'll try to find the figure that we have there. I can't do that now because it digged into my computer. But as soon as I found the figure with the preliminary results, I'll send it to you with some comments on the actual results.
Thank you very much.
Yeah, you're welcome. Thank you for the question.
We had a last question from Alberto.
It's more kind of a curiosity about the interpretation. So would it be correct to say that, so because you have this going down of synchronization when you increase the frequency and then it goes up again, so it looks like synchronization is blocked in the middle frequency range. Does it make sense to say so? And in case, is there any clue about why this happens, or maybe it is known and I don't know.
No, there is a what you can see here is mostly here than in the actual range, is that we are not sure what happens at here. So we are so close here to the Nyquist limit. So I'm not sure what happens here. So what is really stable, and that's why we actually only use these two clusters, because here you can see that there is a peak here, but again, it should flat out. It flattens out, and it remains stable within very specific frequency ranges, instead of this huge ramp up. And the reason for doing that is and it's very specific also for regions, and we can't. We would like to map specific interaction depending on tasks, but we need more data in order to understand whether these peaks changes in frequency depending on the task, or task load or task relevance. Like sleep data would be really important to understand whether these peaks or this activity move in frequency, and if they move in frequency, if this is an actual blocking of as you mentioned earlier, or so there is nothing here, and then we only have bursts of activity when we reach up here, or if these peaks moves around depending on the task.
Okay, I see. Thank you. Also, I really appreciated your first slide, the one in which you had like personal life and work life mixed together, which also seemed to show that your paper is now going to elementary school. It's something I understand very well.
Yeah, something like that. No, one of my papers is going to elementary school. The other two are doing other things.
Okay, thank you.
Thank you very much.
Thank you very much, Gabriele. I think there are no more questions, so another virtual clap.